Welcome to the Net Change podcast, podcast 1. An entomologist is studying the movements of the calculus bug, an elusive and endangered species of insect, to determine its migratory habits. The entomologist is charting a calculus bug's movements along a coordinate axis. G of t is the differential function graphed below. So when you see the words differential function, that's referring to the derivative. Right? Differential means derivative. So we have the derivative graphed. This is the derivative of position, which means it's the velocity curve. So what can we tell about the bug's movements in the graph of the derivative? In other words, the graph of velocity. Right? So if we notice, we see we have an x-intercept at 3 seconds. What does that mean in terms of our bug's movements? We're negative from 0 to 3 seconds, or below the x-axis. We're above the x-axis from 3 to approximately 10 seconds. Right? What's that telling us? So the position in centimeters of the bug at time t in seconds moving along a coordinate axis is s equals the integral from 0 to t of g of x dx. In other words, if we integrate our velocity, if we had an equation here, we integrated velocity, we'll have the position function minus a constant. So let's take a look at the change of the bug's position as a function of time. Because the area under the curve, the area under this velocity curve, is going to give us change in position. Right, so the area under the curve, g of x, is the sum of the area of all our areas here, all our triangles. Right? So we're going to look from 0 to 3 seconds. I have that underneath. So the area under the curve, g of x, the area under the first triangle, is the change in position from 0 to 3 seconds. Notice it's negative. Right? That's a very clear, easy find triangle, right? So we have negative 6 times 3 times a half is going to give us negative 9. Notice that we have that x-intercept means the bug stops. Its velocity is 0. Why would it stop? Because it's turning around. Now I'll talk about that red line that's on there in a moment. All right, so it's turning around. It's moving in a positive direction. So the area under the curve g of x, the sum of the triangle from 3 to 6 there, and the triangle from 0 to 3, notice is going to cancel each other out. Because for 3 seconds, from 3 to 6 seconds, it went in the positive direction. And the amount it went in the positive direction was exactly the same as it went in the negative direction. So in other words, basically the bug, from 0 to 3 seconds, the bug travels 9 centimeters in the negative direction. From 3 to 6 seconds, the bug travels 9 centimeters in the positive direction, and basically returning right back to where it started, right back to the x-axis. All right, so now it's going to keep moving in the positive direction because our graph is above the x-axis. And if we find the area under the curve, we find the total change in position. Right? So from 6 to 6.5 seconds, right? So I've got a trapezoid there that pretty closely models the function. One side is 6, one side is 6.5. So add those together and divide by 2, because that distance there is only 1, means that it's traveled another 6.25 centimeters. So it's still traveling in the positive direction. From 7 to 10 seconds, the bug travels another 9.7 centimeters. So we've got, we're going from 7 to 10, approximately 10 there. And so that would be 3, and then 6.5, and times a half is going to give us 9.75. So for a total distance of 9 centimeters in the negative direction, and approximately 25 centimeters in the positive direction, which means that the total change would be the negative 9 plus approximately 25, so that would give us a negative 16. I also could have done a Riemann sum here. It's a little hard to do the Riemann sum without a function to plug into, and it not being a real easy one to figure out in terms of rectangles. But the triangle is pretty close to approximating that. So that's the total change in position. The total distance traveled, however, maybe I should put it up here. It's a little crowded down here. the total distance traveled, we would consider that we would just add -9, the absolute value of that, plus 25. So that would give us 34 centimeters. Actually, probably put centimeters here. Right? So oops, why did I put a negative? I didn't even see that. Sorry about that. So 16 centimeters is the total change in position, because 9 of it was in the negative direction. 34 is actually the total distance traveled, because that doesn't care whether it's positive or negative. The red line there is the approximate graph of the position curve. All right, so notice that from 0 to 3, he's moving in the negative direction. And he moved 9 feet in the negative direction, so I should be at 3 seconds, I should be at -9, which is where I approximately am. Had to estimate a little bit. And then at 6 seconds, I'm right back where I started again, right at the x-axis. Right? And then after that, he's going to keep moving in the positive direction. Right? So for everything from 3 to 10, notice, has a positive slope. Right? It's the above and below the x-axis isn't the same for the position function. Right? That just is his position. So at 3 seconds, he's 9 feet away from the line where the food is. And then he spends the next 7 seconds moving in the positive direction. Right? But we look at the slope of the line this time. So the slope of the line is positive from 3 to 10, meaning he's going in the positive direction. Okay? He just hasn't gotten back to where he started until 6 seconds. All right, so you should be able to interpret the graph of a derivative about what it tells you about the position of whatever it is we're talking about. In this case, it's the calculus book. And as you're going through this, if you have questions, just write them down. All right, so now we're going to look at the change of the bug's velocity as a function of time. That means we're literally just looking at this particular graph, because this graph gives us velocity. So velocity is negative and decreasing from 0 to 3 seconds, right? Because the numbers are getting smaller. Negative velocity means the bug is moving away from the food direction. The initial velocity is -6 centimeters per second, and then -4 centimeters per second after 1 second, and -2 centimeters after 2 seconds. So, I mean, literally, these y values are just your velocity. And the bug stops after 3 seconds, right, because the velocity is 0. All right, so now velocity is positive and increasing from 3 to 7 seconds. Positive velocity means the bug is moving in a positive direction. The bug's velocity is 2 centimeters per second after 4 seconds, 4 centimeters per second after 5 seconds, and 6 centimeters per second after 6 seconds, and 6.5 centimeters after 7 seconds. That's its maximum velocity is 6.5 centimeters per second, and that's also its maximum speed. Velocity is still positive, but is decreasing from 7 to 10 seconds. Positive velocity means the bug is still moving in the same direction, but the velocity is decreasing because the bug is slowing down, and at 10 seconds it stops. Right? So that's the other information. We can gather information about the position by evaluating the area under the velocity curve. We can gather information about the velocity by just looking at the values of the velocity curve. And by evaluating the slope of our velocity curve, we can gather information about acceleration. So the initial acceleration is constant, 2 centimeters per second, because the slope of the velocity curve here is 2 centimeters from 0 to 6 seconds. Each second, the bug moves 2 centimeters per second faster than the second before. Although the velocity is increasing, the rate at which it's increasing begins to decrease after 6 seconds. So acceleration from 6 to 7 seconds is approximately half a centimeter per second, or I don't know, maybe that says, I think that says half a centimeter per second squared. And all I did was I took the slope. It's approximately 1/2 there. The acceleration is 0 at 7 seconds as the bug begins to slow down. The derivative of velocity is 0 at the horizontal tangent line. So where velocity has a horizontal tangent line, right, our bug starts to slow down, right, because there's a second where it's not speeding up or slowing down. Because the velocity is decreasing, the rate of change of velocity, acceleration also decreases. The acceleration is negative from 7 to 10 seconds. So the rate at which the bug is moving is decreasing. Although he's still going in a positive direction, he's just not doing it as fast. All right, so if I integrate, so from 0 to 6 seconds, right, the acceleration is 2 centimeters per second. So if I were to integrate 2 dx, I would get the equation for the velocity curve, right? Of course, it would be the family of functions, right? Not the specific velocity curve, unless I have a point to plug in, initial condition. So v equals 2x plus c describes the family of functions which have a rate of change or slope of 2. If I take the integral from 0 to 6 of the constant which describes the change in velocity under the closed interval, so in other words, if I integrate and evaluate, I take the definite integral of the acceleration curve, because now the constant isn't going to matter, and I integrate that, right? So 2 dx from 0 to 6 is going to be 2x from 0 to 6. That means the change in velocity is 12 centimeters per second. So that's my change in velocity from 0 to 6. Right? And if we look, we've gone all the way from -6 to 6. There's a change of 12. That seems to make sense, right? And that would be the area under our acceleration curve. So now here's the acceleration curve. Let's look at that. So now if we took the area of that, right, that would be 6 times 2. That's 12. Look at that. It matches right here what we get when we integrate and evaluate. And that's really one of the key features of the fundamental theorem of calculus, that taking that area under the curve gives us that total rate of change. Right? And you can see how those match up. Right? And like I said, if you have any questions, if I'm going too fast and you don't understand something, and you need me to explain something later, just write down your questions. And remember, you can always rewind me. You can pause me, rewind me, write something down. That's one good thing about a podcast. All right, so I would have asked this in class, but so we're just going to ask it here. You're going to find the calculus bug's position using the graph of its velocity. So what I would do, I'd pause the tape, right, and see if you can figure it out, and then I'll move the box and you can check yourself and see how close you were. Okay, and I can show you where the values came from. And if I don't remember if this is in your notes, but if it is, you can write it in, and if not, that's okay. All right, so S of 0, where would the calculus bug's position be? What do you think is under that box? Okay, so make your guess, or write down, I should say make your guess. Write down your answer, and then I'm going to move, and then you'll see if you're right. All right. Of course, it's 0. He hasn't moved anywhere because no time's gone by. All right, how about S of 1? All right, where do you think the bug has traveled to at 1 second? All right, let's take a look. All right, so you just pause. I'm not going to wait because I don't want to stand here. But you just pause while you write down your answer and then check. My answer is, survey says, -5. How did I get -5? In case you wondered. All right, so I'm going to have to estimate my little drawing if we're to draw things here, but finding it will be easy. Oops. Where to draw it, maybe not so easy. All right, so let's just say 1's about there. All right, so I see I have a trapezoid, right? So this side here is at 6. This side here is at 4, and these are both negative. And this, it would be 1. So we would have 6 plus 4 is 10. Half of 10 is 5. So -5 times 1 is -5. So it's approximately traveled -5 units. All right, so try. Need to pull my cord here. S of 2. Where is the calculus bug at S of 2? Okay, hopefully you got your answer. -8. Well, it keeps moving in the negative direction, so it's got to be more than -5. All right, so here, approximately there, a little crooked there. But this one here would be -2. right? Because, and actually this is pretty easy to figure out because I have a constant slope here. Right? So if we can figure out we're going 2 each time, right? So I'm going to be 2 less. So I start at 6, and then at 1 second it's 4, and then the next second it's 2, so forth. All right, and then on this side I'm 6. So I've got 6, and then we have that. So we have 6 plus a negative 2, all right, and that's going to give us negative 8. Negative 8 divided by 2 is negative 4, and then times 2 is going to give us negative 8. All right, so that's the area under the curve. The next one is a super easy one. Hope you don't miss that one. S of 3, where's the bug? Negative 9, right? That's the area under that triangle. The triangle. I didn't make this hard. Right? 6 times negative 3 times a half. Negative 9. S of 4, where is our bug located? See if you can get it right. All right, here's the answer. At negative 8 seconds. Or, excuse me, at negative 8. It's turning back the other way, but it's got negative 9 over here, right? And so at 4, this is going to be 2 on this side. This is going to be 1 on this side. So 1 times 2 is 2, times a half is 1. So it moved 1 more space in the positive direction, which means it's 1 less. It's not as far away from where it started. All right, S of 5, where will it be located? And the survey says it's going to be located at negative 5. So notice it's coming back, and notice it's a constant rate of change. So of course these values match up, right? All right, so you just could add that triangle in, and you've got 2 over here and 4 over here, and so that would be 4. That means you're going to have a negative 9 plus positive 4, and that's going to be negative 5. All right, and of course at S of 6, what's that going to be? Well, 0, right? Because these two areas are going to cancel each other out. Right? So if you were paying attention on the last one, this is really, really easy. All right, S of 7, all right, going to go a little farther. Bug's at 6.25. All right, so we just have to find the area of that trapezoid, and we've got 6 plus 6.5. That's going to give you 13.5 divided by 2, because it's only 1. It's going to be 6.25. And at S of 10, we're just going to have to add in that last little piece. It's going to be at 16. All right, so we've already at 6.25. So for all of this, we're at 6.25. All right, we've got kind of a triangle here. Right, so this is 3, and this part here is 6.5. Right, and so that's going to give us 6.5 times 7, and then whatever that is, times 1/2. So 44 point, wait, what did I just do? Yeah, 45.5, and then divide, oops, why did I put 7? That's only, from 7 to 10 is 3. Excuse me. So 6.5 times 3, that's why the number looks so odd, 19.5. And then divide that by 2, so that's going to be about 10.25, so about 10, a little less than 10, and so that's going to take that up to 16. Or actually a little more than 10, and that's going to take it up to 16. If I did that right. Is that 6.5, and that's 3, should be a little less than 16, well, approximately 16, right, because approximately 16. Because actually that would only be 9 point something. 9 point, I forgot what I wrote down, but 9.75. Oh, but that was 6.25. Yeah, it should be about 16, because that would give us 16. And let's hide all those for some other time. So hopefully that made a lot of sense to you, and you did pretty well with that. That wasn't very difficult, I don't think. All right, displacement is how far is the particle from the start? Right? And it's another way of saying total change in total change in distance, right? It doesn't It doesn't look at it just, if you go in the negative direction, you subtract. It's how far you've actually moved. So if I walk back and forth, and I land on the same spot, even though I've walked a lot, it would be, my displacement would be 0 because my position hasn't changed. So since position, S of t, is just the integral of, when we integrate v of t dt, we can use the start and stop times as the bounds and integrate, and that gives us the change in position. So if we integrate the velocity, we find the total change in position for a specific time interval. If you want total distance traveled, you're going to have to figure out when it's going in the negative direction and take the absolute value of those negative distances. Okay? So you have to figure out where your velocity is going to be negative. All right, so here with the graph, it's pretty easy. How far is the particle from its initial position at t from 0 to 12 seconds? All right, so here it's going negative 20 whatever feet in the negative direction, right? Because the graph, that would be 10 times 4 times a half. And then, nice linear function, pretty easy to find the area under. And then it's moving 80 in the positive direction. So the actual change in position would be 60 feet. So it's 60 feet from its initial position. But if we wanted to know the total change, it actually traveled 100 feet, right? We'd have to take the absolute value of that negative 20, right? So the distance traveled is 100 centimeters. The displacement is 60 centimeters, or feet. I don't know why I put centimeters up there. So make sure you know whether you want total distance traveled or displacement, your distance from your initial position. So total distance traveled is what it sounds like. It's how far an object travels during a time interval. It sounds the same as displacement, but is not. Right? Displacement, if you go in the negative direction, you're traveling, and you then go in the positive direction the same amount, it cancels each other out because you're not any farther from where you started. So here we have a honeybee, and he makes several trips from the hive to a flower garden. The velocity graph is shown below. So the total distance traveled, he went 200 feet from the hive, went to 200 feet to the flower, and then he went 200 feet back to the hive, and then he went 200 feet back to the flower, and then 100 feet back to the hive. So he traveled 700 feet. But he went back and forth a whole lot. So the 200 feet where he's going back again, and the 100 feet where he's going back again, right? He hasn't traveled any farther. He's just gone back to where he came from. So he's actually only traveled 100 feet towards the hive. The rest of the time, just going back and forth. To find the total displacement, position shift from the velocity function, we just integrate the function. The negative areas below the x-axis subtract from the total displacement. So there's no need to worry about where it's positive or where it's negative. You just integrate and evaluate, and that's all you have to do. So displacement is really easy. Distance traveled is a little farther because you have to use absolute value. And you have to make sure that you know where is your velocity negative. So you're actually going to have to solve for that out, which means setting it equal to 0 and figuring out where I'm going to have a negative number. I need to scroll down because we can't see part of it. There you go. All right, so we find the roots of the velocity equation and integrate in pieces. All right, well, we haven't found the area between a curve and the x-axis, but we will. That's our next thing. Okay, so we're going to set velocity equation equal to 0 and find when the velocity is positive and when it's negative, and split it into two integrals. Okay, and wherever the velocity is 0, that's wherever it changes from positive to negative, that's where we're going to split that. Okay, and I have an example. All right, so in the linear motion equation, ds dt equals vt. Vt is a function of time. All right, so your velocity is a function of time, and it's the derivative of the position function. For a small change in time, v of t can be considered a constant. When we add up all those small changes in time, we get the total distance. And that's what we've been doing with our area under the curve. So when we add up all of those small changes, we get our total distance traveled. And as the subintervals become infinitely large and the width becomes infinitely small, we have integration. All right, and that's, so when I was breaking it up into triangles and I'm approximating the area under the curve, I'm essentially approximating the integration. With that, if I have a graph and I don't have an equation to integrate, then I'm going to have to use areas under the curve. When I have an equation, though, according to fundamental theorem of calculus, we can integrate and evaluate, and we're going to get that area under the curve. And it's the same as the limit of our Riemann sums. All right, so this same technique is used in many different real-life problems. All right, so there we can see the difference between displacement. We traveled 60 feet. That was our position, or change in position. But the particle, how far did the particle actually travel? It traveled 100, because now we're going to consider that negative part to be positive. Right? Just kind of reflect it right over the x-axis there. We've got 20 positive. That would actually be, this would actually be the graph of speed. So this, while this one here is velocity, this one here is speed. Okay, so the particle travels 100 feet in the first 12 seconds. All right, so now how far did the particle travel in 6 seconds? All right, I left a lot of the work up here just because sometimes writing all of these numbers down and really keeping track of them when I'm trying to teach gets a little tedious, and it's a little faster if that's up there. You can look at the numbers and evaluate those, and I'll kind of go over them quickly. But really, this is just adding and subtracting. Me spending 10 minutes on adding and subtracting isn't necessarily necessary. All right, so since we want to know how far the particle traveled, we're not looking at displacement. If I just looked at displacement, I could just integrate and evaluate, and that's it. So I have to split it at 2 integrals because I got to watch for where the negatives are going to cancel out the positives, or vice versa. All right, so we're going to, we've got the absolute value of t squared plus 3t minus 10 dt. All right, so how we're going to evaluate that? We got to figure out where it splits. So we just factor that. Okay, that factored is t plus 5, t minus 2. And our sign chart can tell us where it, where it's positive and where it's negative, right? We just plug in a value within the interval, right? So I have 1 at negative 5, I have 1, 0 at negative 5, I have 1, 0 at 2, right? And I just plug in, and what's happening? So between negative 5 and 2, my velocity is decreasing, right? If I plug it, I've got negative velocity, right? If I plug in 0 into my function, I'm going to end up with negative 10, right? That's a negative number, right? So the function is decreasing. And this is referring to the velocity. Where's the velocity negative? And then if I plug in a number greater than 2, all right, I'm going to get a positive number. Now, here, that negative 5 is actually not the beginning of our interval because we're going from 0 to 6. Time is not negative. Right? So everything less than 2, in this case 0 to 2, is going to be negative. So I need to make sure I take the absolute value of that because I am going to get a negative number for that. If I don't split it up, I'm not going to know there's a negative number. The negative is still there. Right? We're still going to have negative area for everything from 0 to 2 when we integrate. It will work out that way. It's just going to cancel out some of my positive, and I'm going to think that that's the total distance traveled when in essence I've really only found the displacement. All right, so from 0 to 2, whatever answer I get, we're going to take the absolute value of it. Okay? We're going to make it positive. From 2 to 6, all right, that's fine. We don't have to worry about it because I'm going to get a positive number. All right, so when we integrate, we're going to get the exact same thing, just what I'm plugging in is different. So when I integrate that, I get t cubed divided by 3 plus 3t squared divided by 2 minus 10t from 0 to 2. So I'm going to plug in 2. I'm going to evaluate that. I'm going to plug in 0 and evaluate that. I'm going to take the difference, and whatever answer it is, I'm going to make it positive. And then do the same thing from 2 to 6. All right, and we got the same function because we're integrating the same thing. All right, so I'm going to plug in. I plugged in 2 here, right, and I got 8/3 plus 6 minus 20. You can see it's going to be negative. And then minus 0. So if I plug in 0, I'm going to get 0. So I put the 0 in on the first line, and then I dropped the 0. And I don't remember if this is in your notes with the work or whether I just have this part. I don't remember. And I didn't go grab the notes to remind myself. I make too many notes to remember everything. All right, and then I do the same thing. I plug in the 6 and I subtract the 2. And this time they're not going to be negative. I'm not going to have, excuse me, I'm not going to have a 0. And the answer is not going to be negative. So I have 72 plus 54 minus 60, and all I did was plugged in and evaluated. And then minus, and notice it's going to be the same thing because I plugged in a 2 again. 8/3 plus 6 minus 20. All right, so now this, when I add 8/3 and negative 20, so 6 plus positive 6 and a negative 20 is a negative 14. And so negative 14 is the same as negative 42/3. So I got here, from 8/3 minus 42/3, I got a negative 34/3. But remember, we have to make that positive. All right, so we have a 34/3. Now it's positive. All right, now we go to the other side here, and what I did was I added the fractions together and I added the non-fractions together, and then I simplified. And sometimes I do that so I don't have to change every single number. So then we have a 72, and a positive 54, and a negative 60, and a negative 8/3, right, distribute, and a negative 6, and a positive 20. So all I did was I distributed the negative, and now I'm going to add up the numbers that aren't fractions, and add that to the one that is. So if I add up all those numbers, I get plus 80, and I have that minus 8/3 there, right? So I'm going to combine the 34/3 and the negative 8/3. That gives me 26/3, and 80 plus 26/3. 26/3 is 8.667. That gives us the 88.667, which is the total distance, the total distance traveled, not the displacement. So if we plug in 0 to 6 into the original, we would get a different answer, right? Because we'd be subtracting that 34/3. So instead I'd get the 80 minus 8/3 minus a 34/3. So this would be 34/3 less than it would be because it was moving in the negative direction from 0 to 2 seconds. So be careful. If it asks for distance, make sure that if it asks for total distance traveled, make sure you check to see if your velocity is ever negative by setting it equal to 0 and doing your sign chart. I want to end this tape on this problem because it's at 32 minutes, and then on my next podcast I'm going to start up with some more problems looking at position and then later at net change. All right, bye.